Hi class, welcome to section 3.5, exponential and logarithmic functions. In our warm-up, we're going to solve each of the following. In number 1, we have log base 2 of 8 plus 2 log base 2 of the quantity x squared plus 7x equals 9. Now instinctively, many of us would look at the fact that the bases are the same on each log, and then look at the fact that, well, we've got a plus sign, so we would condense pretty easily using the product property. I'm going to approach this a little bit differently. And because we see here that the log base 2 of 8 is something we can simplify, I'm just going to turn that really easily into 3, because 3 is the exponent, where 2 to the what? Well, that's 3. 2 to the third is 8. So that then becomes this. We have 3 plus 2 log base 2 of the quantity x squared plus 7x equals 9. I'll subtract 3 from both sides, and it'll end up with 2 log base 2 of x squared plus 7x equals 6. As it turns out, I do still have some options. I can either use the 2 as a power, moving it behind, essentially turning it into x squared plus 7x quantity squared, or you can divide both sides by 2. Dividing both sides by 2 is going to be a little bit more efficient here, so I'll end up with log base 2 of x squared plus 7x equals 3. And then we've got a situation where we can turn this into an exponential. So log base 2 of this quantity equals 3. I'll use 2 as my base, of course, so 2 raised to the right side 3, and that equals x squared plus 7x. Go ahead and set this equal to 0, so we have essentially 2 to the third, or 8 here. If I subtract 8 from both sides, I'll end up with the following. X squared plus 7x minus 8. From here, I'll go ahead and factor. And we see here that negative 8, if I figure that two numbers that multiply to be negative 8, but also their add to be 7, those would be negative 1 and positive 8. We set each respective factor equal to 0, and we see that x equals 1 and x equals negative 8. Now, I'm going to be quick about checking my answer. I could graph to check, but I'll just plug it in as such. So if we plug in 1 here, 1 squared plus 7 times 1, in other words, 1 plus 7, that's 8. So yes, you can take the log base 2 of 8 that we already know to be 3. What about negative 8? Well, if we plug in negative 8, that'll be negative 8 quantity squared plus 7 times negative 8. In other words, 64, because negative 8 quantity squared is 64, plus 7 times negative 8, of course, negative 56. 64 minus 56 is also 8. So both of these answers are correct. Sometimes one doesn't work, sometimes both don't work. In this case, both do work. So that's your answer. Number 2. 5 plus 2e to the 2x times 5e to the 5x plus 1 equals 25. The first thing I'll go ahead and highlight here is, well, because we have the same base here, e, and we're multiplying two things that have the same base, we're going to look at the exponents, keeping in mind what we can do in this case, because that's the case. We can add 2x plus the quantity 5x plus 1. And I'll also, kind of at the same time here, make a note that I will be subtracting 5 from both sides. Your goal should be to get the exponential base e raised to whatever power on the left side, or at least isolated, and then continue with solving. So 2e, again, 2x plus 5x plus 1, that becomes 7x plus 1 if I add 2x and 5x. I subtract 5 and I end up with 20. And then I'll divide both sides by 2, keeping in mind that our goal is to get e to the 7x plus 1 now by itself. So that's, of course, what you get in the next step, 20 divided by 2 being 10. And now I have this exponential. I'm going to go ahead and take either the natural log of both sides or rewrite it simply in natural log form. So natural log, yes, base e of 10, and that equals 7x plus 1. If we go ahead and use our calculators, we'll take the natural log of 10, and then divide that, pardon me, we'll subtract 1, and then we'll divide that by 7. So natural log of 10 minus 1 divided by 7, and you'll end up with this, 0.186. And that's our final answer. Now I do want to take the time to check, not by graphing or even by plugging in, because it's not the nicest number in the world to do so. But I'm going to go ahead and maybe take my x value, or use this particular quantity store as x. You have to store it first, of course, and then type in the original problem, which was 5 plus 2e to the 2x, second natural log, and then we're going to multiply, of course, by e to the 5x plus 1. I do recommend you use parentheses whether or not you have the same calculator as me. And then just hit the enter button. We should see, hopefully, our answer pop up. Yep, we do. We see 25 as the result. So 0.186 is, in fact, a good answer. It is correct. Moving on. Now this is officially our intro. It says the 5 most common types of mathematical models involving exponential and logarithmic functions are as follows. So exponential growth, we have taken a look at this in the past, particularly an unconstrained population growth situation, which we will take a look at. This is one of many exponential growth situations. The generic equation looks something like this: y equals a e to the bx power, where b is greater than 0. And, as it turns out, the generic graph for this will take shape, as you know, as such. Okay, kind of swooping up into the right, from left to right. The next basic kind of function we'll look at is an exponential decay model. Carbon dating is a great example of that. The generic equation, or general equation, would be y equals ae to the negative bx power, where b is initially greater than 0. Now they highlight b greater than 0, interestingly enough. The equation itself, as you see, has a negative in front of it. So it is, in fact, decaying as such, graphically speaking. Okay. All of these exponentials will have horizontal asymptotes, just like we've seen in the past. The Gaussian model, particularly a normal distribution problem, in other words, something you'd see in probability and statistics. The function looks something like this, where you have y equals ae to the negative quantity x minus b squared all over 2 power. Okay. I would not expect you to memorize the Gaussian model formula or equation, and really nor would I ask you to memorize the last two, the log growth model nor the log model. You should understand graphically, though, if I am asking you to take a look at a Gaussian model, that it's going to look something like this, like a bell curve that you would see. The log growth model, in other words, a constrained population growth, and again, here's the equation for that. Looks something like this. And then lastly, the logarithmic model, a magnitude of an earthquake scenario possibly would look something like this. Okay. Typical log or natural log function, actually. So those are the 5 basic types of functions and models you'll need to be aware of. Really only the first 2 you'll need to absolutely memorize those equations, which you probably already do. Moving on. So exponential growth, unconstrained population growth. So we're going to do a word problem here. And here's how it reads. The population P of a city is P of T equals 19,995 e to the kt power, where T equals 0 represents 2,000. In 1945, the population was 9,253. Find the value of K and use this value to estimate the population in the year 2020. So we're going to start off by highlighting a few things here. Okay, so I'm going to highlight the fact that T equals 0 essentially speaks to the year 2000. So we're going to need to go back, which we rarely do in problems utilizing time. We're going to go back to the year 1945, which I'll say, kind of as such, 1945, subtracting 55 years essentially, of course, from 2000 gives us a t-value of negative 55. We don't often see this type of thing, but because we're looking back to the year 1945, when we called 0 2000, it's going to have to be a t-value that's negative. The next thing we're going to go ahead and do is we're going to go ahead and start the process knowing that in 1945 the population was 9,253, and using the equation they gave us, start the process saying 9253 equals the population in the current year, 19995, e to the, I don't know k, but I do know the t-value. Right? Back in 1945, we knew the population was this. So we're going to take this equation, and we're going to go ahead and solve for k. First up, let's divide both sides by 19,995. And we'll get this, 0.463, roughly. Maybe I'll just write down 0.4627. We, of course, still have that set equal to the following, e to the negative 55k power. To solve this particular equation, of course, I could take the natural log of both sides, or I can rewrite it, and that's what I think I'll do here. I'll say natural log base e of 0.4627 equals negative 55k. It is imperative that you leave this number on your calculator, so don't use the rounded decimal. Definitely leave it on your calculator so when you actually take the natural log of the last number, you're not going to have any rounding error. So the natural log of 0.4627 and so on is negative 0.7705. Then I'll take that decimal, of course, and divide it by negative 55. And this is my k value. So k, as you can see, 0.014, that's the value that essentially speaks to the rate. We can kind of think of it as that. Really, r or k are one and the same. Now that's all fine and good, but the question did want to, after finding k, use the value to estimate the year 2020 population. So in 2020, we'll highlight the fact that that's going to be a t-value of 20. Of course, p of 20, back in my original equation, is what I'm going to utilize. So I'll say p of 20 equals 19995 e to that same k value. Again, don't round. We're going to use that same decimal times 20 power. Let the calculator do its thing. So we'll go back and we'll type in 199995. And we'll hit second natural log, and then we're going to raise that to the second answer times 20. All right, you might need parentheses around your exponent. My calculator doesn't require that. Go ahead and let the calculator do its thing, and boom, we get an answer here of 26,461 with a decimal. I'm going to go ahead and round it down so that my final is just 26461. That's the final population that we're looking for. Next question. Carbon dating. Carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal if the half-life of carbon-14 is 5,730 years?